This episode of Engineering the Future is brought to you by Member Perks for OSPI, helping engineers save money on everything from electronics and food to apparel and home improvements. Visit Member Perks for OSPI before you shop and enjoy exclusive savings on brand names both online and in-store.
This podcast is brought to you by OSPI, the Ontario Society of Professional Engineers, the advocacy body for professional engineers in the engineering community in Ontario.
Welcome to Engineering the Future, a podcast presented to you by the Ontario Society of Professional Engineers. I am your host, Jerome James. Today, we're venturing into the mind-bending realm of quantum technology and exploring the seismic shifts it's causing in today's engineering landscape. We'll also be discussing the exciting opportunities it presents in both seasoned engineers and the bright minds of tomorrow. Our guest today bridges the worlds of law and quantum engineering. Tina Decker is a lawyer specializing in intellectual property and technology law. She also holds a degree in nanotechnology engineering from the University of Waterloo, and she has completed her master's degree with the Institute for Quantum Computing. Tina, welcome to Engineering the Future.
Thank you. It's great to be here, and I'm really looking forward to our conversation today about quantum computing. My goal today is to make it accessible and understandable so that our listeners, regardless of their background, will be able to maybe learn something interesting about this exciting field.
Well, that sounds like a laudable goal. Let's make it happen. So let's jump right into it. Tina, the world of law and quantum engineering seems like strange bedfellows. Can you tell us a little bit about your journey and how they're connected?
Yeah, for sure. So as you mentioned, I started in engineering. I started in nanotech, and then I did a master's degree. And in most of that time, I had no concept of ever becoming a lawyer or entering law. But during my master's degree, I started getting interested more on the commercialization aspect of technology and of quantum technology. And I came across the idea of like patents and being a patent agent and intellectual property and what that means for creators of technology and developers of technology. And so I ended up speaking with some lawyers and some patent agents to get an idea. And that led me on this path of sort of approaching the quantum industry from more of this business and commercialization aspect, focusing on intellectual property. And then as I went to law school, so I went to the University of Ottawa, which has a really robust law and technology program, I realized that there's also a lot of interesting issues and problems that need to be addressed on the policy side with respect to technology. And so it was a really nice way for me to actually merge my background in engineering and in specifically my experience working with quantum devices in the quantum field and merging that with my studies in law and kind of understanding how I can and bring them together, which is what brings me here today.
Great. And for those who are listening who aren't familiar with quantum technology, can you explain how quantum computing differs from classical computing? And what potential applications does it offer to working engineers and future engineers?
Well, I'll start by explaining that when we talk about something that's quantum versus something that's classical, we're really referring to which scientific equations, rules, and phenomena govern how that thing behaves in the world. So when we talk about something that's quantum, it's referring to things that involve quantum physics, or you'll sometimes hear the term quantum mechanics. And this typically applies at a very small scale. And I'll make a side note here, like one of the reasons I got involved in quantum because of my nanoengineering degree, which involves studying matter at a very small scale. So on the scale of like a billionth of a meter, 10 to the minus 9, this is the scale of things like atoms and molecules. And this is where quantum properties start to become really relevant. So coming back to it, in terms of a quantum computer and what that means, quantum computer is quantum because it is leveraging quantum mechanical phenomena to compute things. And it does this using what we call qubits. And so if you Google quantum computing, that's usually where the conversation starts. Well, we have these things called qubits. And so qubits are a core hardware component of a quantum computer. So it's a physical thing or a structure that exhibits quantum behavior. And we sometimes call this a quantum system. And this can be something like a subatomic particle, so an electron or an atom or something with, properties that fit into the quantum physics model. And so there are different ways that you can actually realize a qubit physically. And, it's one of the things that companies are really trying to do is find out, which physical implementation is going to work best. But the essential property of qubits that allows them to be used for computation is that we can actually prepare them to be in a state of 0 or 1, or prepare it as something in between 0 and 1, where it has properties of both. And we call this a superposition. So a qubit can be prepared in a superposition of both 0 and 1. And if we contrast this with classical computing, we have a classical bit, which can be 0 or 1. It can be heads or tails if you're flipping a coin as an analogy, but you can't really have anything in between. And so the consequence of using qubits is that we have computational power that scales differently in a quantum computer than the computational power of a classical computer. So a quantum computer scales exponentially based on the number of qubits, and this exponential computing power enables quantum computers to solve certain mathematically complex problems more efficiently than a classical computer.
So it's not that they're solving different problems, they're just solving problems more efficiently, or are they actually structured in a way that they can solve problems that a classical computer could never solve?
So it's both, actually. I think the easiest way, so like if everything that I said just went over the heads of our listeners, which is understandable, quantum computer is basically a new type of supercomputer. So we're unlikely to ever use it for things like checking email, but we can use it to solve new problems, things that we weren't able to solve before. And in some cases, we can use it to solve problems that we can solve using classical methods, but that are very, difficult to do or resource intensive to do. So it's both.
So what are the current challenges and limitations of quantum computing? How might these impact its integration into the real world through engineering projects, or might be overcome in the future?
So this is an important topic because we're seeing a lot of big promises in media about what quantum computing will deliver, but far less information on how and whether we can achieve these goals. So the reality is that there are some significant technical hurdles or challenges that have to be overcome to realize quantum computers with the capabilities we're very excited about. And when we talk about applications of quantum computing, the list is almost endless. We have things in material science to like logistics and optimization. At the end of the day, quantum computers are really good at solving problems that require a lot of iteration or have a lot of possibilities, which you can imagine touches on a lot of different possible fields or areas and a lot of different industries. And so we're seeing a lot of promises, a lot of, quantum computing is going to help us tackle climate change. We can develop better batteries, we can, simulate things better. And, I'm confident that we are going to realize some of these goals, but it's not quite so easy as that. And so I'll start by saying that, one really important aspect that I think a lot of engineers will understand is that a computer is a lot more than its hardware. We have hardware and software. And right now in media, there's a lot of focus about how many qubits the next quantum processor from the big tech companies has. So, have we reached 100 qubits? Have we reached 150 qubits? But that's really only part of the story. So while the number of available qubits is certainly relevant to computation, I just mentioned, it gives us that exponential computing power. What's more important is actually the quality of the qubits. Quantum systems are really sensitive to their environment. So even just, fabricating and creating a qubit physically takes already a lot more effort and work than what it takes for us to create our typical classical computing hardware. And this can include the supporting infrastructure as well. So most of the quantum processors that we have today either rely on cryogenics, so being at a very low temperature, or complex optics. So there's a lot going on just to realize the qubit and prepare it in the state so that it can do computations. And then once you have it, go ahead.
Oh yeah, no, you're on a roll there.
Yeah.
I just want to understand the idea around these qubits and the quality.
Sure.
You're saying that we have systems that have up to a couple hundred qubits right now. What is the state of the art of a system today that's doing calculations?
Yeah. So right now we're in the NISQ area, NISQ, noisy intermediate stage of quantum computing. And so that's around like the 100 to 200 qubit range. And so this is what a lot of the big companies like IBM and Google, their quantum processors are in this range and moving upwards. They all have, some pretty grand plans about accelerating the number of qubits they can add to their processors. And that's great. But there's actually a really interesting paper that came out earlier this year that on the archive that highlighted how many qubits and what they're using for. And in most cases, for actual computations that people are doing, and this is happening mostly on the research side, you're using less than that. Like I don't remember the exact numbers, but I want to say it was in like the 10 to 50 range for the types of calculations and simulations that they're doing in the research space right now. And so it comes back to this idea that, we can have 150 qubits, but, if they're not high quality or, there can be other factors that come into play, you might not actually be getting effectively 100 qubits or 150 qubits. It might be less than that. And so that's one of the challenges.
Right. That sounds like a big challenge. How many qubits are required to, say, destroy cryptography as we know it today?
Yes, the big question. My understanding is it needs to be on the order of around 1,000 qubits. I don't know the number off the top of my head, I have to admit. So we're not there yet, is the answer. But to put that into context, I know some of the companies are expecting to reach the 1,000 qubit mark sometime in the next 5 years. Or that's their plan. Whether they get there, we'll see. And so, I think most people would say that it's probably a bit, even if they reach that number, whether they can actually break our current encryption frameworks, it seems unlikely that that's going to happen in the next few years, but we have to entertain the possibility. And what I like to say is that, we do have brilliant engineers and scientists working on these problems. So even if the predicted timeline is later, there could be a breakthrough discovery that we need to be prepared for. So we're not there yet, but the scientists and researchers, they're working towards it.
Absolutely. So those are the technical challenges. What about the ethical or legal challenges or legal conundrums that surround this new technology?
Yeah, there's a lot to unpack there. And it's not just with quantum computing, but I think all quantum technologies. We have quantum sensors and communications, for example. And when it comes to the legal and ethical side of things, I think we're falling into a similar trap that what we're seeing with AI. So there's a lot of investment going into the quantum industry right now and research, and it's generating a very competitive R&D environment. And it's in these situations that we see ethics and responsibility sort of cast aside in favor of being a first mover. And what's happening is that, quantum computing has a very broad application space. And so it can touch on a lot of different industries. And there's this sense that whoever is the first to sort of realize some of these promised applications are going to reap the most benefits from it. And this is actually creating a very interesting geopolitical climate globally as well, because there's a lot of tension between countries who want to collaborate and, foster international collaborations because the quantum community is diverse and is global, but there's it's competing a bit with the sort of national security aspects and more nationalistic focus of, being an independent nation with, our own quantum computing capabilities so that we can realize the most economic benefits for our country above others. And so it's a lot to unpack here. I co-authored a very long paper actually on this subject that published earlier this year. What we have to be conscious of is the inequalities that this is creating, right? So if we have this sense of first movers, right, we're already seeing that there are some countries who have and some countries who don't. And there's a big risk that countries who are already, behind on technological development are going to be even further behind as quantum computing becomes integrated more and more into real world applications. And so these are things we need to be alive to in terms of what the societal impact is, what the global impact is, and what the consequences of that are.
Is there a quantum computer race right now? Who are the big players in this race? Is it nation states or giant tech companies?
Yeah. So the notion of a race, I mean, a lot of people say that there is a race right now. I'm not a big fan of characterizing it that way because I think, to my point about the legal and ethical aspects, I think it leads us to a lot of sort of negative mindsets about, sort of having a single supreme country in this technology space. And I don't think that's very constructive at a national or global level. But the big players, as you might imagine, are, of course, the US and China, and most of the big quantum computing advancements are coming out of these countries. But there's also, I mean, we're in Canada. We have an amazing quantum ecosystem here, and we have some companies that are doing really well. Xanadu, for one, D-Wave, who are really trying to innovate in the quantum computing space. And so while there is a race, I mean, I think Canada's a perfect example of this. While there is a race, I think it's not the whole story because, Canada, for example, is never going to compete with the US just by, the fact that we have a much smaller economy, we're a much smaller quantum community, but we have certain strengths that can contribute to the global quantum ecosystem. And that's, Canada has a very robust and long-standing foundation in quantum research. And that's, having an impact globally in terms of the talent that's being produced to innovate in this space. And so, yes, there is a race, but it's not the whole picture because even, a smaller country like Canada can still be a huge player in the ecosystem, even if we don't have all of the best and all of the top quantum computers.
Very interesting. As quantum computing technology progresses, what skill set and knowledge should engineering students and professionals start acquiring to prepare for widespread adoption in the industry?
Yeah, so for engineers at any stage of their education and career, I think the first step is to develop a basic literacy in quantum computing, which I respect is easier said than done. But to understand that quantum computing exists as a tool to solve certain types of problems. And so that knowledge involves, I think, understanding, what problems quantum computers can solve, and perhaps more importantly, what types of problems they can't solve. And so at the educational level, I think for, our engineering students and, upcoming students, even at like the high school level, it comes down to integrating hands-on experience so that students who end up in research labs or industry remember that they have this tool in their problem-solving toolbox. And for professionals, it's really the same goal, but instead of learning about what quantum computer offers in, their education in school, because they're past that, they'll have to engage with other resources to upskill their knowledge. And I mean, there are a lot of resources out right now, almost too many in a sense, online in terms of books and courses where you can learn the basics of quantum computing. And so, yeah, I think the first step is getting that base knowledge. And we're already seeing too at the educational level, like there are universities who are trying to develop either quantum science or quantum engineering degrees at both the undergraduate and graduate level. I mean, even when I was at the University of Waterloo, they've offered since before my time as a master's student, a specialization in quantum information for graduate students. I had quantum mechanics as a core course in my nanoengineering degree. And so I think that integration with other programs, like existing programs, as well as the development of new programs, is really going to help the future talent in the quantum engineering space. And then for professionals, they might have to, either take advantage of online resources, or we're starting to see now also the emergence of quantum consultancy groups. And so, so their role is then that they offer as a paid service, of course, quantum education together with strategic advice in how, you can apply the quantum computing knowledge to your project or business. And I think that's something we're going to see more of emerging, and even from engineers, actually.
And do you see this as a pivotal time in the grand scheme of things within quantum technology? What if you had one piece of advice to give a student today, what would it be?
That's a good question. I think my piece of advice would be to, consider it as an option. I think we saw, maybe a decade ago or even more, people were talking a lot about getting the core programming skills. And I know when I was entering into university, a lot of people said, well, you should learn Python, you should learn this, it's going to help you later on in life. And I feel like we're at a similar moment. It's not exactly the same, but we're at a similar moment with the quantum field where, students or professionals who are interested in, don't be afraid of it, test it out, see if it's something that you're interested in or something that might help you in your career or in your business or on a project. Because I think what's holding back or what a barrier can be is the fact that the quantum field comes off as very esoteric and niche, and it is to some extent, but it's becoming more and more accessible as more and more people are getting involved in it. So yeah, my advice would be to, try it out and try learning about it and see if it's something that might interest you or benefit you.
We talked a bit about the opportunities quantum computers will bring going into the future, both negative and positive impacts, the effects on current cryptography, being able to factor super large prime numbers instantly. What are some of the other applications for this technology in the future? What are the areas scientists are excited about exploring?
Yeah, so there are a few examples that come to mind on that. And one industry that's starting to, I guess, connect with the quantum field is the telecom industry, which may not be the first thing that comes to mind. But in March, Ericsson Canada actually announced the launch of a new quantum research hub in Montreal. And this is in partnership with the University of Ottawa and the University of Sherbrooke and their quantum institutes at the universities. And the goal of this collaboration is to apply quantum computing methods to telecom networks. And so they're looking at applications in distributed computation, secure communications, quantum networks, so the idea of like a quantum internet even, and also quantum-inspired protocols. And so that's one example. I think another area that I've been seeing more and more like news articles about and updates is the automotive industry. So I have one example here. In 2019, Volkswagen worked with the Canadian company D-Wave to demonstrate a live traffic routing system that relied on quantum computing.
Oh, interesting.
And the car company is also investigating quantum computing applications to improve their manufacturing and assembling processes. You can also use quantum computing to improve simulations of fluid dynamics, for example. So, I mean, in the automotive context, that can be helpful in terms of saving costs of, tunnel testing. And I mean, generally, quantum computing, with the predicted simulation capabilities, we're expecting that that's going to save us a lot of time in testing things, whether that's simulating something like fluid dynamics or trying to devise a new drug or a new material. I mean, with these simulation capabilities, we're expecting that we can spend more time, on the engineering aspect and less time on the lab trying to test things out. And then one other field that I think is really worth mentioning, if you don't mind,
absolutely,
is the field of quantum machine learning. And this is something I'm still learning about a bit, and it's starting to really grow, I think. And this could involve, sort of one of two things as I understand it, which is using quantum computers like a neural network. So training a quantum computer to solve problems like a neural network would, or using quantum computing to train classical neural networks. And so I think it's going to be really interesting, given how much we've seen AI expand in the last few years, to see how the field of quantum machine learning, develops. And it's something I'm definitely going to be keeping an eye on.
Can you talk about some of the safeguards that are being developed as well in this unknown era of quantum computing on the horizon? How are engineers helping us safeguard data moving into this future?
Yeah, when it comes to safeguarding our data, quantum computing is actually the threat here. And there's a lot to unpack about why and how quantum computing is a threat. And as I mentioned, some of that could be on a technical side, but it could also be on like a societal or ethical side. But the gist is that future quantum computing methods, as you mentioned earlier, are expected to break our current encryption frameworks, which protect almost everything we do right now with our data or internet actions. And so it's a bit of a slightly controversial subject because not everyone agrees on the extent to which quantum computing is a threat, if at all. But I can offer my perspective, which is that I take a proactive view. So I care less about whether it's actually possible to break our existing encryption frameworks, and I care more about being prepared for the possibility. Like I said, we have some amazing researchers who are working on these problems, and a breakthrough discovery could radically change our perspective on what's possible and when. And so, I'd rather be in a position that we're ready to secure our data in the event that there is a cybersecurity risk rather than waiting for it to happen. And so this is where the concept of post-quantum cryptography comes in, or PQC. And post-quantum cryptography is about exactly that. It's about improving our encryption frameworks to be secure against a quantum-enabled cybersecurity attack. And so the National Institute...
I've been hearing the concept of quantum safe being batted around. And is that as in that same vein?
Yes, it's exactly this. So when we talk about being quantum safe, it's about protecting ourselves from a quantum-enabled cybersecurity attack. And so there's actually standards in development right now through the National Institute of Standards and Technology, or NIST. And so they, over the last few years, had put out a call for proposals and received submissions and did reviews on some new algorithms and encryption frameworks that are considered quantum safe. And so they're actually, as far as I know, very close to finalizing their first set of standards to implement this. And some companies are already implementing some algorithms and encryption frameworks to be quantum safe, but it's just a question of whether it's standardized yet.
So it's almost taking a theoretical approach of, we see where the technology is going, what is possibly capable if we were to get 2,000, 3,000, a million qubits working. This framework that we're developing will actually safeguard against whatever into the future going down that direction is developed?
Yeah. I mean, I'm not an expert in encryption, but that's my understanding. We can develop these algorithms that, based on our knowledge of what quantum computing can achieve and the types of problems it can solve, you can get very mathematically robust about what kinds of problems and how hard they are and whether quantum computing methods will do it and using which algorithms. And so using that knowledge right now, researchers are developing these new algorithms and frameworks to protect against that theoretically, but it has to be an adaptive and dynamic process, right? Because as the technology advances, we're going to realize maybe new capabilities and new discoveries. And so I think there'll need to be a bit of a change in how we implement things like standards to be a bit more agile so that as new threats become evident, we're in a position to respond to them quickly. Because the reality is that, migrating systems to new encryption frameworks is a very intensive thing to do. It takes years to fully migrate, all of our digital systems, something that's to a new standard. And so we have to be alive to that because the threat landscape may change. And so when we're talking about quantum computing and encryption, it's really all about risk management. We need to know people are working really hard to figure out, how much time, how much money, and how much effort needs to be put in to mitigate these risks in a reasonable way. And it's an issue that's important, for both our public and our private sector organizations. And so, it needs to be adaptive.
For sure. Can you speak to any legal implications? I mean, whether or not it's easy or hard to hack into a system, you're going to still face the same legal threats as a hacker, correct?
Yeah, most likely. I think the consequences will probably be the same if someone's caught doing this. But I think it'll be interesting to see, if we do experience a quantum-enabled threat, if that happens or when that happens. I don't know how it's done. So something I've been thinking a lot about is how right now a lot of quantum processors are being made available through cloud services. And so this is a great thing, actually, and I'm generally in favor of this because it opens up quantum computing to everyone, really. I mean, everyone who can access an internet connection. I mean, there's still inequalities at play here, but anyone who can access an internet connection and, you can access a quantum computer today if you want. Like, you can go on IBM's website and I think a few others and access a quantum computer. So the question that I have at the back of my mind is, how can we moderate access to quantum computers so that we can, be proactive in mitigating risks, because we don't want malicious actors to take advantage of these publicly available services. So how do we moderate that access while still keeping it open to people so that, we can have our high school students and go on and, try get that hands-on experience that I was talking about earlier, and have our undergraduate students and so on, there's a bit of a push and pull there, and I don't know what the answer is, but they're questions that we need to think about.
We've covered a lot of ground today. Is there any final ideas, final thoughts that you'd want to leave our listeners with in thinking about quantum technology into the future?
Yeah, absolutely. So I truly believe that quantum can be for everyone. It's certainly an esoteric field, but there's no reason for it to be exclusive. And whether you're a student or a seasoned professional at any stage in your career, I think there are a lot of interesting learning and career opportunities in this field. And we're lucky here in Canada to have such a robust quantum community to offer these opportunities. But there's also a lot of room for growth, not only on the technical development side, but also in terms of diversity and how we shape Canada's quantum ecosystem more broadly. And so my hope is that people from different career stages and different disciplines and different backgrounds will get involved with the quantum community and with quantum industry so that we can continue to innovate to benefit our society.
Wow. For something so small, Tina, it's an incredibly big topic, isn't it?
Yes, indeed.
Thank you so much for sharing your time and expertise with us today.
Thank you.
And thank you again to our audience. If you haven't already, please be sure to subscribe and leave a comment. We love hearing from you. I've been speaking with Tina Decker, lawyer and nanotechnology engineering graduate from the University of Waterloo. I'm your host, Jerome James. You've been listening to Engineering the Future, and we'll see you next time.
From all of us at OSPI, the Ontario Society of Professional Engineers, thanks for listening. Please be sure to subscribe so you don't miss an episode.